There we go. All right. So this was the way you were going to remember to distinguish between the atomic number and the mass number. Right? Atom is small, so it's atomic. Mass is big, has massive in the name. Okay. And that takes us to our final kind of review, which is the number of neutrons, because there is no number of neutrons on the periodic table. Right? None of the numbers on those little squares will get you the number of neutrons. We are now talking about isotopes. The number of neutrons is going to be important because isotopes are elements that have a different number of neutrons. So we need to know what we're dealing with and how to get that neutron number. Anybody remember how to do that? How do you find the number of neutrons? We talked about it in the first unit. Alexis?
It's probably wrong, but don't you like subtract the atomic number from the mass number?
It's like so not wrong.
Oh,
Yay. Yeah. You subtract the two numbers that you do have, right? And so, again, this is important because atoms of the same element can have a different number of neutrons, like carbon 12 and carbon 14. One has 6, one has 8 neutrons. That's important. And these are called isotopes, not ions. Ions deal with changing electrons. Isotopes are changing number of neutrons. And we also said that isotopes are named by the element followed by the number of neutrons. So you just heard me say carbon 12 and carbon 14. Well, this is the mass number. And you don't have to get it out, but on your periodic table, the big number for carbon is 12. So this is the normal. This would be the isotope. You wouldn't know which is which if you didn't look at your table and see what is the given mass number for carbon. We can't have all the isotopes on the periodic table. That would be like a periodic book. It'd be huge, and it wouldn't be useful. So that's why only one version of the element is listed on the periodic table. And then if it's the isotope or even the ion, if you're talking about it being charged, you have to determine that another way. And the way to do that is by looking at the mass number. So we'll name the isotope by saying carbon 12 or carbon 14, and then from there you can figure out how many neutrons it has. And just like Alexa said, you just subtract the atomic number from the mass number, and that leaves you with your number of neutrons. Here's why. The mass number is protons and neutrons together. Atomic number is just protons. And so if you take the P plus the N minus the P, get rid of the P's, you're left with N, the number of neutrons. Simple. Just subtract the two numbers you do have. All right. You have a cloud bubble for this. At the bottom of your periodic table, it has this, right? It shows it. So, always be using that. It's a resource. So if I say, hey, there's a cloud bubble, you're looking, it's probably the one on the left or the one in the middle. Both of those are going to be helpful. Okay. All right, so isotopes. These are atoms of the same element with a different number of neutrons. So I know this is a little bit fuzzy, but these are all, this is hydrogen, this is helium, and this is lithium. I know that because I am looking at the number of protons. 1 proton is hydrogen, 2 protons is helium, 3 protons is lithium. Okay? And then there's it shows a total of 3 versions of hydrogen. This would be deuterium, and this is tritium. But here the mass number is 1 because there's only one thing in the nucleus. Here the mass number is 2 because there's 2 things. Here it's 3 because there are 3 things. You add up the protons and neutrons. And the same thing here. These are both heliums because they have 2 protons, but here it's 1 neutron, so it has a mass number of 3. Here it has 2 neutrons with the 2 protons, so it adds up to a mass number of 4. Right, same thing here. You add these all up to get 6, you add all these up to get 7. It's still lithium because you see the 3 protons is constant. Okay. We will come back to that video. So let's look at, this is kind of our first major new idea. Obviously, we introduced the strong force, which is what's keeping the nucleus together. But let's look at radiation when a nucleus does not stay together. So in an unstable nucleus, it's going to emit radiation in the form of very fast-moving particles with the energy to produce a new nucleus. So it's not that the neutrons or the protons get destroyed. They do not like melt down or like disintegrate or just vanish. What it means is the nucleus gets rearranged. So the number of protons and neutrons now gets shuffled up and changed. And if you change the number of protons, you are changing the element that you're dealing with, right? And so you get a new element, right? It changes to another one that it wasn't before. There's 3 types of particles that get released during nuclear radiation. There's the alpha, the beta, and the gamma. Okay. We've mentioned alpha particles back when we talked about the gold foil experiment, where they shot those positive alpha particles through the gold foil and watched to see what happened. And so we're going to talk about this very briefly. We could have a whole unit on radiation, but here was just a brief introduction to it. And so what you're going to need to know is how strong these are and what they can go through and not go through, right? And so these elements undergoing nuclear radiation are considered radioactive. Even if they're totally safe, it's still the process of radioactivity or them being radioactive, even if they're emitting perfectly safe forms of radiation. So there are 3 types of radiation given off during an unstable nucleus's decay process. They have different penetrating abilities. So the alpha particles, they get stopped by skin. They cannot penetrate your skin. The beta can go through skin, bone, but they get stopped at aluminum. And then the gamma can go through, human bone, flesh, skin, aluminum, but they get stopped at lead. And we'll look at another one where they get stopped at concrete. So obviously, which one are the strong form of radiation? What's the strong type based on this picture? Allison? The gamma, right? The gamma. Good. And then what's going to be the weakest one? What do you think, Maddie? The alpha. Good. Here's another picture. If this is the radioactive source, the gamma rays, and you can see the gamma rays actually move like this, kind of this transverse wave up and down. So they can go through paper, aluminum, but they get stopped at concrete. So that's why on the Bill Nye, when they were talking about housing that nuclear waste, they talked about putting it like in 10-foot thick, big, huge containers, or almost look like kind of like silos. And it would contain that material, obviously, unless there was some kind of like earthquake, right? The beta gets stopped at aluminum, and here it's showing like skin or paper stops the alpha particles, so they're pretty weak. And we will backtrack and watch a couple videos that talk about this and kind of show what's going on. But really with radiation, this is all I need you to know. Like the gamma's the strongest, the alpha's the weakest. Concrete and lead stop the dangerous gamma rays. Aluminum and lead will stop, aluminum stops the beta, and then paper and skin, the alpha can't even penetrate through them. Okay, so on the Bill Nye, it introduced this concept called half-life, and it's the amount of time that it takes for half of the atoms in a sample to decay. And so the half-life for an element is a constant. It is unique. So each isotope has its own half-life, and that can range from seconds to millions of years. And it doesn't depend on the number of atoms that are present. So it's just half of the sample. So whatever the sample is, half of it. Okay. And it doesn't matter how long it has been around either. A couple of years ago, I was looking for something and this popped up and I was like, oh, that's kind of funny. So I just put this little, we'll watch this, maybe. Okay, maybe not. See if I can get it later. So on the Bill Nye, he showed the bottles that had like the red dye in it, and he was like, it was like full strength, and then he cut it in half, and it got a little bit fainter, and then he cut it in half and got a little fainter, like diluted it by half as he went down the line. And each time he diluted it by half, it was going through one of its half-life cycles. And I believe he was showing uranium at the time. And it was like 24,000 years was the half-life. So every time like he diluted it in half, that was 24,000 years. And then he diluted it in half again. And it took all those cycles of diluting it in half to get it to be where it looked pretty clear, like all the dye was gone, meaning that all the uranium had decayed and was now safe. That's what half-life is all about. It's basically you're taking half of that sample and it decays and goes from being radioactive to having half the isotopes non-radioactive, like where they've already decayed and become stable again. Right, and so it's important to remember is that you're not just looking like at a single radioactive atom. So I can't look at a point and be like, that one is going to decay and become stable. Like we can't predict which atom in a sample is going to do that. But in a whole sample, you can say, okay, half of them in this amount of time will have gone from radioactive to non-radioactive, or that nucleus will have decayed and rearranged itself and now it is stable. Because that's all it is. It's unstable and it's going to stable. It's working its way to being stable. All right? And so that's kind of a key thing. You're only looking at the sample in general. You can't pinpoint a specific atom out of that sample. And so when you examine the half-life of an element, you're really looking at the sample and all the elements that are in that sample. So if you look here, if this is what you're looking at, this is your original sample amount, and it's showing the full amount. Whatever that is, it's the full amount. And then in its first half-life cycle, so here it's showing at 8 days, half of the sample is decayed. So its half-life is 8 days. So every 8 days, like clockwork, half of that sample that is remaining is now decayed and not radioactive. So it's all radioactive, now half of it's radioactive, and then in another 8 days, that half is now only the part that's radioactive, and then in another 8 days, half of that, and then another 8 days. So it keeps cutting it in half every half-life that it goes through. All right, whether it's days, hours, minutes, years, it goes like clockwork. And the half-life is the time it takes for half of that sample to decay. So we don't care how much of the sample you started with, cut it in half, that amount of time is the half-life. Good? Half-life is a really simple idea, but sometimes people try to make it more complex or confusing than it really is. This is something that you're also going to see again next year in biology. I know last year Mr. Trainer was like, oh goodness, it's like these guys are struggling with half-life. So again, sometimes people just try to make it more complicated than it really is. And I'll try to give you easy ways to kind of keep it where it makes sense. So if you have a calculator, you're going to need to bring it. I have some, but yours are better than mine. So typically people prefer to use their own. So if I was you and you don't normally bring your calculator, I would be bringing it here for the next little bit. Okay. So I'm going to give you, there's two types of problems we're going to see. I'm going to tell you how to go about solving both of them. And you just have to make sure you follow the steps, and it's pretty straightforward. There's not really many curveballs that you can get. So for most problems, you're going to just have to determine how many half-life cycles a sample went through, and then use that information to answer the second part of a problem. And there's two ways to determine how many half-life cycles a sample went through. The first one is the problem might give you 2 time values. So like a total time, and then how long an isotope's half-life actually is. So if you see 2 times, like 2 hours, 2 seconds, 2 days, 2 minutes, if you see 2 time values, you're going to go about solving the problem one way. And I'll show you that. It also might give you a problem where 2 sample amounts are given. So like 2 milligrams. Like you have a milligram and a milligram. You have a gram and a gram. Right? If you're given 2 sample amounts, then one that the sample started at, the bigger one, and then one that the sample ended at, the smaller one, you're going to go about solving this problem a second way. So these are the 2 types of problems. Either 2 times are given or 2 sample amounts are given, and then you just follow different paths based on which type of problem you're given. So here's what it looks like. This is slide 26. So barium-122, again, that's how we name the isotope. So this is the isotope of barium. It has a mass number of 122. So that 122 is not part of the math. That is part of the name. Right? And it has a half-life of 2 minutes. You have a sample of 80 grams. After 10 minutes, how many half-lives have passed? So what do you see in this problem? Oh, second part. And how much of the barium sample is left? So solve part 1, obviously, to answer, and then you have to use that to answer part 2. So what do you see 2 of in this problem? Do you see 2 time values, or do you see 2 sample amounts? What do you see? Owen, what do you see? 2 times or 2 samples? Yeah, I see a 10-minute and I see a 2-minute. Minute and minute. That's 2 times. Okay? So 2 minutes and 10 minutes. That's the first step. Now, once you recognize that you have 2 times, this is how you go about it. So it's the same problem, I just have it here again. So take your total time, which was what? Was that 10 or was that 2? Allison?
2.
Are you sure?
I don't know. 10?
10, right? So you have 10 minutes total. And then it says it has a half-life of 2 minutes. So you divide your 10 minutes total by your half-life, which was 2. So time of 10 minutes divided by the half-life of 2 minutes. This is going to give you how many half-lives it went through. So 10 divided by 2 is 5. So that is the answer to part 1. That's pretty easy, right? Your total time divided by what the half-life is. And this is how many half-life cycles it went through. So it went 2 minutes, 2 minutes, 2 minutes, 2 minutes, 2 minutes, which is 2 minutes times 5, which gives you a total of 10 minutes, which is what the problem said. All right, so that's part 1. Now, we have to answer part 2. So slide 29, we're answering how much of the barium is left. Well, we're still dealing with the same amount, or the same problem, and it says we started with 80 grams. So we started with 80 grams, so we have to cut that in half 5 times, right? Half-life, think of like dividing by 2, cut it in half, cut it in half, cut it in half. So here's how you do it.
This is from Miss Castro.
Okay. Got it, thank you.
Yep.
All right, so we have to cut or divide by 2. How many grams did we start with? What do you think, Josie? 80, right? So we had 80 grams. How many times do we have to cut it in half? How many half-life cycles did we go through? 5, right? So we're gonna take our 80 and cut it in half 5 times. So on your paper, you have 80 divided by 2 gives you what? 40. And then 40 divided by 2? And then 20 divided by 2? 10 divided by 2? 5. And then 5 divided by 2? 2.5. Okay. So, to check to make sure you divided by, cut it in half, which is dividing by 2, a total of 5 times, this is where people go wrong. They either do like 1 too many divisions or they don't do it enough. Always count 1, 2, 3, 4, 5 times you actually divided. On your paper, when you start doing these, you need to write this. People are like, oh, I'm just gonna put it in my calculator, I'll keep track. You don't, you mess up. Write it out. I'm gonna be giving you points for showing your work. If you don't show your work and you get it wrong, you're getting double the points taken off. You have to show your work because I'm telling you, you will get confused. Yes?
Why did you show your work? Do you still get points or do you get none?
If you show your work and you get it wrong, then you get the points for showing your work.
Alright.
Yeah. So this did get divided by 5, or divided in half 5 times. Right, so it's really easy to divide too many or not enough. So your final answer is 2.5 grams of the barium is left after the 10 minutes have gone by. Now, is 80 divided by 5? Anybody have a calculator out? What's 80 divided by 5?
I'm pretty sure it's 16.
Okay. Check it.
I don't have a calculator.
Addie's checking. 16. Look at you. You're just on a roll today. Is 16 the same as 2.5?
No.
No, not even close. So just because you go through 5 half-lives, that's not the number you divide by. You don't take your sample and divide it by the number of half-lives you have. Half-life is cutting in half. So you have to cut that sample in half 5 times. Not 80 divided by 5, 80 cut in half 5 times. It's different, okay? All right, let's look at practice problem number 2. Phosphorus 32 is an isotope that has a half-life of 14 days. There is a sample of 64 grams of phosphorus that is decayed to 8 grams. How many half-life cycles has it gone through, and how much time did it take for this to happen? So again, this is a 2-part question. That 32 again is not part of the math, it is part of the name. It is the name of the isotope for phosphorus. So it has a mass number of 32, and that's why we have that number there with phosphorus. So the first thing you have to do is solve part 1 first, then use that to solve part 2. So you have to ask yourself, what do you see 2 of? Do you see 2 time values or do you see 2 sample amounts? Like 2 types of grams? Dorian, what do you see? 2 times or 2 samples?
Samples.
Yeah, because I see 64 grams, which is 1 sample, and I see 8 grams, which is another sample. Grams and grams, that's samples. All right, so here's how you do a 2 sample problem. It's a little different than the first one we just showed. So, take your starting amount of the phosphorus. So the bigger value. So is that 64, Liam, or is that 8?
That's 64.
Yep, 64 is the bigger amount. So take the bigger amount, and now we have to cut that in half, or divide by 2, until we reach the smaller amount, which is an answer of 8. So we're going to have to cut 64 in half until we reach an answer of 8. All right, so on your paper, I have it set up for you. 64 cut in half 1 time is how much? What's 64 divided by 2?
30.
32. Good job. 32 divided by 2? 16. And then 16 divided by 2 got us to our answer of 8. So we're starting at 64. We're trying to end at 8. And you're like, Okay, now what? Well, you want to know how many half-lives that took. So we just count them up. Each half-life is cutting in half or dividing by 2, so just count how many times you divided by 2. 1, 2, 3. So your first answer is it went through 3 half-life cycles. Count how many times you divided by 2 or cut it in half until you reached 8, and it was 3. So that is your answer. It went through a total of 3 half-life cycles. Okay? And from there, we answer part 2. Alright, so how much time did it take for this to happen? Well, according to this problem, how long is one of its half-lives? Cypress, how long is a half-life? What's it say right here?
14 days.
14 days, very good. So 14 days, how many of those half-lives did we just determine it went through? What was our answer to part 1? Good, 3. So what can you do? Close. 14, 14, 14, so what do we want to do? Multiply, right? So 14 times 3, right? And that's what we do. We think of what we know. How much time did it take for this to happen? Cypress told us it was 14 days. So this phosphorus went through 3 half-life cycles. That's what we just solved for. So if we went through 3 half-life cycle, each half-life cycle is the 14 days. So we want 14, 14, 14. So instead of adding them 3 times, let's just multiply. 14 times 3. So 3 cycles of 14 days each. It's that key word for multiplication, each. And so 3 half-lives times 14 days per half-life is going to give us a total of 42 days. So it took 42 days total for this to happen. So the math is simple. It's just you have to remember what to do. Okay? All right, so we're going to stop there. I have the one video that I want to backtrack to.